welcome back to my channel. Thank you so much for joining me again. I hope you're all having a wonderful day. I certainly am. So, what are we doing today? Today, I want to talk about the notion of a partition. So what is a partition exactly? A partition is just a way of dividing something. So when we're talking about the partition of a set, we're dividing the set up into smaller, non-overlapping parts. So that's basically what it means to be a partition. So let's look at a few example problems, the kinds of problems that you might get on an exam or a homework assignment, and try to work through them together. So let's get started.
So let's say that we are planning a wedding and we want to plan out the table arrangements, the seating arrangements. And let's say we put all these red guests on table 1 and all the blue guests on table 2. Now, the nature of this task means that we never assign a guest to 2 tables at once. The guests are either on the red guest table or on the blue guest table. So there's this dividing line between them, right? So let's call this one set A and set B. Because no guest is assigned to 2 tables at once, the intersection of A and B is the empty set. There is nothing in the intersection of A and B. So these types of sets have a special name. We call them disjoint sets. So let's look at the definition. Sets A and B are disjoint if and only if, that's what the if with 2 F's means, if and only if the intersection between A and B is empty. So this is what we have here. We have 2 disjoint sets of guests because no guest is assigned to 2 tables at once. So far, our definition of disjoint just referred to 2 sets that don't overlap. But of course, we can have a situation where multiple sets are disjoint. So let's look at this diagram here. So this kind of diagram represents what we call a cluster analysis, where we get lots and lots of samples of data, then we plot them along various dimensions and see which samples are like other samples and which samples are different from other samples, and then try to put them into clusters. So this is one particular kind of cluster analysis. Let's say, for example, the clusters could be anything, but let's say, for example, that we are taking measurements of different flowers in our garden, and then we're finding that we have 4 distinct sets of flowers: the green set, the yellow set, the blue set, and the purple set. When we think about this in terms of disjointness, now remember our definition of disjointness, so 2 sets A and B are disjoint just in case, if and only if, their intersection is empty. So if we have our definition of disjoint in mind, we can see that all 4 of these sets are disjoint. Any pair of these 4 sets are disjoint. So this is a very particular kind of situation where any pair of 2 sets are disjoint. So we have a special name for this. It's called mutually disjoint. So let's look at the definition of mutually disjoint. So say we have some series of sets, A1, A2, all the way up to AN. So this set of sets would be mutually disjoint. So that's the term we're trying to define. If and only if, now remember IFF, that means if and only if, AI intersect AJ is empty for any value of I and j. The only condition is that they're not the same. So for example, if I was 1 and j was 2, we would say that A1 and A2 have an empty intersection. So basically all this is saying is that if we choose any pair of sets, we will find that they have an empty intersection. Their intersection is empty. So let's look at an example problem. So let AI equal the set containing I and I squared for each integer I equals 1, 2, 3, 4. Okay, so let's start right there and figure out what A1, A2, A3, and A4 are. A1 equals the set containing I, so I is 1, and the set containing I squared. 1 squared is also 1. So we get the set containing 1 and 1. Now we know that repeats don't count, so this just amounts to the set containing 1. A2 is the set containing I, which is 2, and the set containing I squared, which is 4. A3, the set containing I, which is 3, and I squared, which is 9. And then finally a 4, which would be 4 and 16. Okay? Now, the first thing we want to do is we want to find the union. So another way of writing this would be using the big union sign. We've seen that a couple of times. The union from I equals 1 to 4 of AI. So all I'm doing is just writing the exact same thing up here, just in a more condensed notation. Okay, so what would the union be? So it would just be literally just be all the elements that appear in any one of these sets. So it would contain one. All I'm doing is just going through the members which appear in any of these sets. So 1, 2, 4, 3, 9, 4, and 16. Now we know repeats don't count, so we don't need the 4 there twice. So this would be our answer for A. Now let's look at the intersection, which is B. So the same thing, let's use that big intersection notation. So I equals 1 to 4 of AI. Now again, all I'm doing is just rewriting this, but in a more condensed notation. Okay, so the intersection would be any element which appears in all 4 sets. So looking at these 4 sets, there are no elements which appear in all 4. The closest we come is 4, which appears in A2 and A4. To be in this set here, you need to be in all 4 sets, so nothing meets that condition, so the answer to that is the empty set. Okay, the last question are A1, A2, A3, A4 mutually disjoint. Now we know from the last slide that mutually disjoint means that we pick any two pairs in these 4. So A1 and A3, A2 and A4, A2 and A3, any pair we like. If we pick any pair, their intersection is not empty. So to disprove that some set of sets is mutually disjoint, all we need to do is find one pair, just one pair, which is not disjoint, which has a non-empty intersection. It has something in the intersection. And we can see that A2 and A4 both contain 4. The intersection of A2 and A4 is not empty. That means the condition for these 4 sets being mutually disjoint is not met. There is a pair, namely A2 and A4, which have a non-empty intersection. Therefore, the answer is no. These 4 sets are not mutually disjoint. So let's look at a new scenario. So say we are doing this cluster analysis. So we're putting all these data samples into different sets. So we have a yellow set, a green set, a blue set, a red set, and we actually have a little purple set up here. An added feature of this analysis is that we have these little blue X's. So let's assume that the blue X's are what we call outliers. And what we mean by that is that they don't get assigned to a set. They're not assigned to a set. So we've got the yellow set, the purple set, the green set, the blue set, and the red set. So the question is, are those sets mutually disjoint? And the answer is yes, right? Because if we pick any pair of those 5 sets, including the little purple set, there is no sample, there's no dot which appears in 2 sets at once. There's no dot that's in simultaneously in the red set and the green set. So these sets are mutually disjoint. But that's not the end of the story. We have this added feature of the outliers in this diagram. So let's say that S is the set of all samples, and then we have 5 sets, purple, yellow, green, red, and blue, and we'll just call them A1, A2, A5. What we find is that if we take the union of sets 1 to 5, right? So that's all 5 of these sets, purple, yellow, green, red, and blue. We find that it does not equal the set of all the samples, because there are all these blue X's, which are outliers, which means that they aren't assigned to one of those sets. So in fact, the union of all the samples which are assigned to sets, so the union of A1, A2, A3, A4, and A5, is actually a proper subset of S. Okay, so we have a particular scenario here where we have mutually disjoint sets, but if we take the union of those mutually disjoint sets, we don't reach the set of all samples. We've still got leftover outlier members which aren't assigned to one of those 5 sets. Let's look at a different scenario. Okay, here we have the same distribution of data samples, but we just have a different assignment of the samples into sets. But what you'll notice now is that we have a different number of sets, right? So we have gray, pink, red, and blue, and then we have these little sets, light blue, that looks like sort of like a salmon pink color, green here, and yellow here. So this is the same distribution of data, but the assignment of the data to sets is different. What we see now is that we don't have any outliers. We didn't assign any of the samples as outliers. Every sample got assigned to some set, even these samples which got assigned to sets on their own. Now we have a different situation. We have a different number of sets, for instance. We have 1, 2, 3, 4, 5, 6, 7, 8 now. Let's call these sets B, just to differentiate them from the last example. Now, if we take the union of I equals 1 to 8, right? So this would be B1, B2, B3, B4, B5, B6, B7, B8. So if we take the union of all the B's from 1 to 8, we find that it does equal S. It does equal the set of all samples. And the reason for that is that we don't have any outliers. So this kind of scenario where we have mutually disjoint sets like these 8 sets, they don't have any members in common, that cover the entire space of possibilities. If we take the union of all these disjoint sets, we exhaust the space of possibilities. We don't have any elements left over which aren't assigned to any set. So there's a special name for a scenario like this, and it is called a partition. A partition. Let's look at the definition of partition. Partitions are always ways to divide up a bigger set. So if we have, this circle represents some set S, a partition will always be a way to divide up S into different subsets. So these sets here, A1, A2 to AN, however many sets we want to divide S up into, the requirements on those sets is that if we take the union of all those sets, we end up with S. So what that means is there are no outliers. If we connect all those sets together, we don't have anything left over. And then the other requirement is that all of those component sets of the partition, A1, A2 or AN, are mutually disjoint. That means there's no element which appears in 2 of the sets or 2 or more of the sets simultaneously. So this would be a perfect example of a partition, right? So there are 8 sets, all of them are non-empty. If we take the union of all 8 sets, we end up with the entire set of samples, and then all of the sets are mutually disjoint. They don't have any members in common. So this would be a perfect example of a partition. Okay, let's look at another example problem. So let E be the set of all even integers and O be the set of all odd integers. Is the set containing E and O a partition of Z? So Z, or Z, if you remember, is the set of integers, right? Okay, so what would that be? So we've got 0, 1, 2, 3, 4, and then it goes all the way to positive infinity. Then on the other side, we've got -1, -2, -3, -4, and that goes all the other way in the other direction as well. Now, what we want to do next is we want to divide the integers into even and odd, and we will signify even by just putting a red circle around it. So we've got 0, we've got 2, and we've got 4, we've got -2, and we've got -4. And then for odd, we'll do it with the green circle. So we got 3, 1, -1, -3. And then that pattern continues all the way from negative infinity to positive infinity. So the question is the set containing E and O, is it a partition of the set of integers Z? Okay, so to be a partition, we need to meet some different conditions, right? If yes, then, so E and O need to be not non-empty. So that's satisfied, right? Because both sets already have members in them. The even set has all the red circled members in them, and odd has all the green circled members. So they're both not empty. E and O are disjoint. If this set of sets is a partition of a bigger set, then these sets need to be disjoint. They need to have no members in common. And this is true, right? So this one is true, and this one is true as well, because they don't have any members in common. Okay, and then the last thing is that if we take the union of the component sets making up the partition, if we take the union, it should equal the bigger set. So what this would mean is that the sets E and O completely exhaust the integers, right? There are no integers which are neither even nor odd. So no integers will fall outside one of these two sets. And that is true, right? There are no integers which are neither even nor odd. Now, I said it really depends on what you consider 0. So in this case, we're considering 0 as an even number. So that means there are no integers which are neither even nor odd. So this condition is met, which means that the set containing E and O is a partition of Z. So yes. If we considered 0 to be neither even nor odd, then these two conditions will still be met, right? So E and O are still not empty, and E and O are still disjoint. There's no integers which are both even and odd. So if we considered 0 to be not even, then this third condition would not be correct, right? Because if we took the union of E and O, there would still be a number left over, namely 0, which doesn't fall into either category. So this condition would no longer be correct. So E and O would no longer be a partition of Z. So E and O being a partition of Z is conditional on considering 0 to be even, which is a standard assumption anyway. So I think we're all in the clear there. Okay, let's look at another example. So let's say that we've got this housing plan. So let's say the red dots represent furniture that we're, planning to buy or that we've already bought for our house. Let's call the entire set of items of furniture, we'll call that H for house. Say we want to divide the furniture up into a partition. So let's say we make a horizontal line. We make a horizontal line across the house. We're dividing the house up into the north and south halves of the house. And then let's say that the set N represents the items of furniture in the northern half of the house, and the set S represents the furniture in the southern half of the house. So NS is a partition of H, right? Because they're not empty, they are disjoint. There's no item of furniture which is simultaneously in the north and southern halves of the house. And N union S equals H. So they meet the condition for being a partition. Okay, but say we wanted to further divide up our furniture along this axis here, so this orange axis. Now we have four sets of furniture. So with the further division, we've got the northwest, northeast, southwest, and southeast. What we find is that northwest, northeast, southwest, and southeast is also a partition of H, right? They are non-empty, they are disjoint, and their union equals H. So the union exhausts the entire space. There is no leftover elements. Okay, so we have two partitions. We have the partition N and S, which is a two-way partition, and then we have the four-way partition northwest, northeast, southwest, southeast. This is a very particular kind of scenario which we call a refinement. So let's look at the definition of what refinement means. X and Y are two different partitions of a set S. X is a refinement of Y, right? So one of the partitions, so this one or this one, is a refinement of the other one. So X is a refinement of Y if and only if, right? IFF means if and only if. Each element in X is a subset of an element in Y. Okay, so let's see if our example here with the furniture counts as a refinement. So let's say that the four-way refinement, so this one, counts as X, and the two-way refinement is Y. So X is a refinement of Y if and only if each element in X is a subset of an element in Y. So let's see if this is true. So the first element of X is northwest. So northwest is this set here. And northwest is a subset of north, right? Because north is this entire set of furniture items here. Likewise, northeast, which is this set here, is also a subset of north. Then southwest, which is this set of furniture items here, is a subset of the set south. So the set south is this set of furniture items here in the southern half of the house. Okay, so southwest is a subset of south. Likewise, southeast, which is this set here, is a subset of south as well. Okay, so it seems that every element in this partition is a subset of an element in this partition. Okay, so what is a refinement? So X is a refinement of Y if X is a finer grained way of dividing up the set. So Y here, this north and south division, is a coarse grained way of dividing up the set of furniture in this house, whereas this four-way partition is a finer grained way of dividing up the set. Okay, let's look at another example problem. So let's see be a set representing a deck of cards. Which of the following are partitions of C, and which example is a refinement of another? Okay, and then it's telling us to ignore jokers. And then if we've got the suit in boldface, that means the set of members of that suit. So heart in boldface is the set of hearts. And then if we've got the number or the value of the card in boldface, that's the set of cards with that value. So Q in boldface is the set of queens, and so on. Okay, so we want to know which of A, B, and C are partitions of C, and which example is a refinement of another. We just need to look at what are our definitions. What are our definitions of a partition? So the component sets of a partition, they have to be non-empty, they have to be disjoint, and when we take their union, it exhausts C. It exhausts the bigger set. It exhausts C. No leftovers. Okay, so those are our three conditions for being a partition: non-empty, disjoint, and the union exhausts the bigger set. Okay, so let's just go one by one. When we look at A, we've got all four suits where our sets are the set of hearts, the set of clubs, the set of spades, and the set of diamonds. So all of those are non-empty, right? So each of them have 13 members, so they're all non-empty. They're all disjoint because no card can be simultaneously a heart and a club or a club and a spade. And then the union exhausts the set of cards. So that's also true, right? If we take the union of this set, so the union of this set, it equals the set of cards. So A would be a partition. Partition. Okay, what about red and black? Well, it's very similar, right? They are non-empty, they're disjoint, no card is simultaneously red and black, and the union exhausts the set of cards, right? So if we take the union of red and black, it equals the set of cards because there are no leftover cards. There are no cards which are neither red nor black. So this is a partition as well. And then finally, this one, which is dividing up the sets by their value. So 1 or ace, and then 2, blah, 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 10, jack, queen, king. So all of those sets are non-empty, right? They're all disjoint. There's no card which is simultaneously a 2 and a 10 or a 10 and a jack. And then the union exhausts the set of cards, right? Because the union of all of those is the set of cards. There's no card which doesn't fall into one of these categories. So this is a partition too. So all three of these are partitions. All three of these are partitions of the set of cards. The second part of the question is saying which example is a refinement of another. So let's test if C, so this set here, 1, 2, blah, 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 10. So 1, 2, is this set a refinement, let's say red and black? So if this set is a refinement of this set, then every set comprising this partition has to be a subset of one of these. So if we take, for example, the set of aces, it has to be a subset of red or a subset of black. So we know that is not true, right? Because if we have a set of aces, we have 2 red ones and 2 black ones. So this set here, the set of aces, is not a subset of red or a subset of black. And this actually the same thing goes for every element. So for example, the set of queens, again, we have 2 red ones and 2 black ones. So the set of queens is not a subset of red and not a subset of black. So in this particular case, the partition of the set of cards by their values is not a refinement of the set of cards by their colors. So here the answer is no. Okay, but what if we tried a different one? So what if we tried heart, club, spade, diamond? Is that a refinement? Is this a refinement of red, black? So if we know our set of cards, we know that the set of hearts are all red. So the set of hearts is a subset of the set of red cards. Likewise, the set of diamonds are all red too. So the set of diamonds is a subset of the red cards. On the other hand, the set of clubs are all black. So the set of clubs is a subset of the black cards. And the set of spades are all black. So the set of spades is a subset of the black cards. So in this particular case, it does meet the definition of refinement. Every set here in this partition, the partition by suit, every set in this partition is a subset of one of the sets in this partition. So if we have this square represents a set of cards, and we've got the red cards, which are hearts and diamonds, and we've got the black cards, which are clubs and spades. The partition of cards by color would be this division here, right? So we've got the reds on the left and the blacks on the right. But the partition of the set of cards by suit would be a refinement of that partition, right? It's a finer grained division of the set of cards. So this is a case study from this paper by Donald Knuth. So he is talking about this kind of party game that people played in 16th century Japan. So basically what happens is that you burn 5 sticks of incense. And then the game is that everyone has to guess which sticks of incense were the same and which were different. So for example, let's say you burned, this blue incense, then this sort of reddish one, then this orange one, and then a blue one again, and then finally this green one. So the object of the game is that guests would have to correctly identify that the first stick of incense and the 4th stick of incense were the same scent. So in this Donald Knuth paper, he talks about how in the 16th century Japan, they could represent this game by using these kinds of diagrams. So in this particular one, we have 5 sticks of incense, and then this horizontal line is showing that these 3 sticks of incense are the same, and then these latter 2 are the same. So we have 2 sets two sets of sticks of incense, and these two sets of incense create a partition of the bigger set of 5 sticks of incense. In this diagram, the first and third sticks of incense are the same, and then the second, fourth, and fifth are the same. So this is also a partition of the 5 sticks of incense, dividing them up into 2 sets. So Donald Knuth also goes on to demonstrate how these kinds of diagrams were used to represent the 52 chapters of the Book of Genji, which is this classic work of Japanese literature. So each of these diagrams represents different ways of partitioning the sticks of incense. So for example, this one has the first 4 as one set, and then the last one as a different set. Or this one has the first and last stick of incense as one set, and then the second, third, and fourth as another set. So all of these are different ways of partitioning up this set of 5 sticks of incense. And then these kinds of diagrams were used as this sort of symbolic language to represent the different chapters of this great work of literature. So it's a kind of pretty interesting historical application of this theory of partitions that we've been building. And it shows how these theories of math that we've been using can be used to create these beautiful works of art. So I think it's a pretty interesting application of the theory. Okay, the last concept I want to talk about is this concept of the Bell number. So what does that mean exactly? So if a set A has n members, the Bell number B of n is the number of possible partitions of A. So let's look at a really easy example. So say we have a set of 3 members, A, B, C. Let's try and think of what the possible partitions of A, B, and C could be. So one would be all the members just in sets on their own. One would be putting A and B together and leaving C. We could also put A and C together and leave B. And we could also put C and B together and leave A. And then finally, we could just have all the elements together. So the Bell number for this set of 3 members is 1, 2, 3, 4, 5. Here's a table of the Bell number for sets of various sizes. Okay, so if we have the empty set, the Bell number is just 1, right? Because there's only one possible partition, that one. Then if we have just one member, there's only one possible partition, which is just the set itself. If we have 2 members, we have 2 possible partitions. We could have the set itself, and we could have the 2 elements in sets by themselves. And then 3, we've already drawn that one. That's the one here. And then you can see as the numbers go up, the Bell number really increases dramatically, right? So 3 gets 5, 4 gets 15, 5 is already up to 52, and then 8 is all the way up to 4,140. So the amount of ways that you can partition a set increases dramatically when the number of elements in the set increases. Here's a really interesting diagram which I found on Wikipedia. So this is a set of 5 elements, and it's showing how all the different ways that we can partition this set of 5 elements, we're visualizing that, and it turns out that we can get 52 different ways of partitioning this set of 5 elements. So the Bell number of 5 equals 52, because there are 52 ways of partitioning a set with 5 elements.
Okay, so that's about it from me. Thank you so much for joining me once again. And please remember to like, subscribe, hit the notification bell, help support the channel. And I will see you next time. So have a wonderful day, everybody. Bye.